just a list or a table. And then Nolan's going to tell us something about the overall, this NIDM structure, this normative data model representing provenance in normative data analysis. And then we'll show us some details on the most sort of developed part of this NIDM thing, the part that represents results. And then I'll wrap it off by actually showing you that paper where actually, oh, and then I'll do it in clarity then because it's not paper where we actually have something. And then Chris wanted to say something about durable, because the idea is that we're going to link these two things together so that you can export your data analysis from any arbitrary software and it'll be represented in the same common way, which makes Chris's life easy when he's trying to suck results from around the world. Back to cycle.
That is not So I'm just going to give you a quick introduction to the session. It's been something like how many years now? 3 or 4 years? That the INCF, which is the Neuroinformatics Organization based in Stockholm, has set up this program that is basically realizing how much is lost and how much opportunities are lost using with unshared data, and also badly shared data. And that's the two things that we're trying to work on, like put the incentive of the community to share the data, so work with the funding agencies, work with the editors of journals, work with these guys, the folks, and also work with the community. And one of the things that I think is important, so I'm just going to say it, it's maybe not specifically relevant to the session, is that there is this mindset that many of the people who acquire data think that because they acquire the data, they own the data. And that's one of the big problems that the community has to sort of work with, because it's usually funded by public money, universities, or grant agencies, and basically we have to shift like the mentality, the mindset of the community thinking, okay, if I acquire data for research, for finding things, because in the field of I'm working on requires that we need more data to be out. And there's a lot of really big incentive for doing that. You've seen a lot of the non-reproducible research being presented. I'm sure that you're aware of that, so that's part of that, of the problem. So because there's there's very poor reproducibility in many of the neuroscience fields, and especially I would say in brain imaging and in brain imaging genetics as well, you really need to get more data and more power and more the community to be able to reproduce and replicate results. So that's the motivation of this task force that that Dave Kennedy at the back and myself started a long time ago, and then came up Satra with the semantic web ideas, and then and we're going to show you what we are now at what we are now, and it's I think there's a bit of an ideal here. There's a bit of something that we never reach. And there's a little bit of something that is happening at this kind of event, and is really going to change I think the face of neuroimaging. That's the hope and the excitement that I have about it. The other thing I want to say is that it's horrible to set up standards. I mean, we've seen like we've seen like in many cases that it's not one tool to group them all. But it is absolutely necessary that we spend the time, and even if it's a bit of a slow-going process, to make it right and happening. Because if we don't have good standards for sharing the data, it's going to be yet another sort of sequence of 5, 10, or 20 years of mess before there's something else that will come up. So, I mean, I feel like we have a responsibility not to waste this opportunity. I mean, we've got some funding and organization to back us on the trying to design a good model to be able to share data, to share more data and more adequately. So that's something that I want to share with you, that we have this responsibility to make it right and make it good. Yes, I think that's the whole thing about motivation. So as Tom was saying, there will be like a little bit of something on the data acquisition that Nolan has been working. So how do you describe data? And he's been working on the extra stuff and with Cookie, I think, and other stuff. So you're going to show that. Then Safran, I think, is going to show you also the semantic web stuff, right? And what are the basic tools and basic ideas? How do we share? How do we capture and query things after that? I mean, what's the underlying tools for that? Then I think Camille is going to show the model that you came up with the group for SPN and for FSL. And Guillaume is there as well. If you want to chime in, Guillaume, you'll be very welcome. Go ahead. So between FSL and SPN, we've got the first stuff, and Thomas has been very pushing things forward on that. And then work with and how this capture metadata is going to end up in your board, and how your board is going to interact with that, and what it's going to bring to the community. And then Tom will finish by a few queries on the models. I think that's the plan. So yeah, so unless you've got questions right now, let's get started with Nolan, if you're ready.
One comment. So you're talking about data sharing and how we should sort of do that. The one thing, I deal with big data all the time and big groups, and the one thing that I constantly hear and I kind of identify with to some degree is how complicated it is to sort of let go of your own data. So what often happens is, somebody will, a group of people will collect data for years maybe, and really dedicate their time and effort towards it. And then suddenly a bureaucrat from somewhere will say, give us your data right now, so that someone else can data mine it and produce results that you've worked on for so long. So for me, it's always trying to find solutions to incentivize people to actually freely give up their data to the world at the right time.
Absolutely. No, and I should have said with the thing that I don't think we have the set of mind that I don't think people that require data, Michael doesn't really know something have a set of mind that they are proper and they have the ownership of the data. I think that's the wrong set of mind. That's people that are almost like a psychological basis that try to go through, and you have to think about what's your job, what is my activity, what do I work for. That's one of the things. But I should have said it's absolutely critical that we find the right place to do the incentive and the positive incentive. Yeah, I don't believe very much in state thing. They may be good for but I don't believe that very much. But having like an acknowledgement that this is a good data set. There's a publication like Michael was presenting this morning with publication associated with that. Publication is going to be cited heavily, and that's the right thing to do, right? You're building your science on the previous stuff that is cited. You're going on the shoulder of giant on that. Data is a critical thing. And if you're acquiring data with a set of mind that you're going to put that on the web, you're going to communicate. That's a communication you're doing in the sort of in the scientific community. You're going to be much better. You're going to be very careful of the quality control. You're going to have to feel like you're sort of you want to put the best thing out. A bit like if I'm designing an algorithm, I'm going to try to be designing a good algorithm. If I'm going to acquire data and publish it. If I'm going to acquire data, I'm going to acquire good data. That's a very big incentive, I think. That people will get the recognition for good work in this field of data. But having like the set of mind that you're sitting on the data and you're going to make the most of application of it because that's your career sort of trip. That's the thing we collectively have to think. That's probably not the right way of doing it. And that's a difficult message, and you have to balance.
I think it's about offering them, sorry, I think it's about offering people solutions to counteract those individual, those are real concerns and fears, right?
Yeah.
I mean, your whole life is based on some data that someone else that publishes. That's a real issue, regardless of what they should do morally or not, right? So it's about giving them tools, incentives, publication possibilities, standardizations, all these terms to get them to voluntarily do that and they see the benefit.
And we also have the grant agencies that think the money and we will get we could have. So those sorts of things. But you're absolutely right.
I think it's a wrong problem because if you get enough people to share the data, the advantage of it will become clear after 2, 5, 7 years, and then you get more and more people using it. But if you get yeah, but you have to get a community that can share actively and in a way that
we're not there yet. I wish we were at that stage, but it's not. I've been looking and Jason's been looking for a data set with using genetics. You've got like a bit of a free, a good policy for data sharing. You mentioned genetics. I was able. I have a big task. Yes, ask many people in the field. I know many people in the field, and many would say yes, we would like to do that. Oh, it's not ready. We can't. Oh, there's a site, and it's a multi-site thing, and there's one site that doesn't want to do it. It's a pretty dire situation at the moment. Frankly, there's great initiatives, but if you're working on something a bit specific, or you're working on something like that, it's a difficult. We're very far from getting this.
We are looking at across all these different scales of the analysis process. So our issues and concerns and characteristics for the raw data sharing. There's also the metadata and results and the processing and the things that are underlying your publication that all also need to get into this sharing mindset. Those get a little bit beyond some of the because there's different issues about why I might share my raw data and why I might share my family result that goes into the paper that I publish. And we got to work on all those barriers. And maybe some of those are less harder to overcome than the original raw data too. So I think tool some more streamlined.
But the right people are Michael. Yeah. That's the right people. That's the thing that Michael is going to make things moving probably more quickly than we are, because I think it's necessary that we do what we do so that we can eventually federate data sets and query across things, and I think that's absolutely necessary. That's going to be really hopefully very useful. But this example is the right thing that makes the community move, I think, more quickly. So we have to get more of you.
So just to kind of give you a practical answer to what kind of cards can provide to data sharers, there's this idea.
Can you speak louder?
Oh, do you want
So to give you more practical, better way, I'm going to shout now. So give more practical solutions before. So give more practical solutions to how to incentivize people to share data. So here working also Michael and Daniel to popularize the form of data papers. When you publish your data set as a publication, and if your data set is really that important, it's really so groundbreaking, it's going to get cited a lot, because a lot of people are going to use it, a lot of people are going to do analysis based on it, and therefore you're going to get credit recognizable within this academic community. So we thought that this might incentivize people to share the data.
Yeah, we like for some studies we create boilerplates so everyone that's involved and those that get cited at the end of the author list. There's sometimes issues with that, but that's one way of doing it. People often want to get that first paper out so that everyone cites the initial paper study. So there's usually like a lag that needs to be there. Okay? 1 year lag from the time you finish collecting data. And so there's ways to maybe find a balance or find ways to get people to do it. But
sometimes it's embargo for several years. Given the situation we are in at the moment, it much better than what is happening. So, but that's a topic.
One thing I'd say is, I think the greater reality is, I mean, having given some of our own data sets away and before we ever even got to touch them, it's just rare that someone really feels all that scooped. Usually what happens is the data is going to be analyzed. I mean, even now with, when we do an internal release, look for our public releases for the FCGNG stuff to work out problems and so forth, you don't really see people rushing to the data. And it's, I think people's fears are a lot more, the reality is data sets are really analyzed enough. The fear is that someone's going to leave me out. You also don't have to share everything. If you have something special in your data set, you can keep that aside as long as there's an impact to data in some way. And then everyone gets to that standard core piece, and you have something on the side if you can do something special with. That's very true.
All right, so
I think everybody can hear me, right? So I think it's always good to start off with an XKCD slide. Can everybody read it? Or load up? Oh, I don't think I can blow up an image. So I'm going to talk about a standard which isn't really the next standard. It was a standard that existed about 16 years back. The semantic web and its underlying data model, the RDF, was created around 1998. Computers and tools weren't fast enough to handle many of the complexities that it did, but the idea was a structure that scaled much like the web. And so when I was told that I should give an intro to semantic web, I said, I'm not going to prepare any slides because there are enough introductions to the semantic web. So instead, I'm just going to go through not 102 slides in this, but hopefully in the next 8 minutes or so, a subset of this that gives you a flavor of what the semantic web really is about. By the way, so this is from Semantic University, which was started by Lee, who's a co-chair of the Sparkle Working Group, as well as the VP of Technology at Cambridge Semantics, kind of down the road from where I am. So, since we are on an admin team in some sense with the challenge going on, these set of slides seem kind of appropriate. And some intent behind the semantic web was to be able to answer questions like this. And if you enter this, this was done in 2011, I've repeated this query earlier today. Google will return a lot of hits and 0 results. It cannot understand that. Even though Google is working on some components that we would say is a semantic web. You go to PubMed, there's still a lot of searches, search results, no answers. You can go further into specific databases, which are all these siloed pieces, and you still get hits, but no answers. And then finally, once you get to a set of linked scientific data, you start getting a few answers popping up. So, as Lee says, what's the trick? And the trick, as you'll get to see in the context of some of the work we're doing in brain imaging, is agreement on common terms and relationships. We're not talking about tomato and tomato. We're talking about various things that we use very loosely. And English is a very loose language. But when you actually boil down to it, you can't understand that there are subtle differences that each of our choices is because they're biased by things that we think about. So one thing is, can we agree on common terms? We may disagree on the definition, but we could at least create two IDs. This is definition 1 of this thing, and this is definition 2. And when we use this term, we use it in this context. Second, we need an incremental and flexible data structure. And it turns out graphs are very flexible data structures. And so we'll be built up on that. There needs to be good enough modeling and a query interface tailored to it. So the next few slides, I'll go through some of this. So what is the semantic web? Essentially, this. That's a tree, that's a shirt, that's a pant, that's a cat, that's a dog, that's a house, that's a door, that's a garbage can. Together with the garbage can is in front of the house, the man is in front of the tree, and that's what we're talking about, representing information in a way that discusses the elements and their relationships with each other. In terms of branding, so the term semantic web, I guess, was coined in the late 90s. There's a Scientific American article by Tim Berners-Lee and Lara Husser. Which talked about the promise of this thing, and it kind of got overhyped over the years. And we haven't reached that question that we can answer about Alzheimer's. More recently, it's been given terms like the Open Graph Protocol by Facebook, Knowledge Graph by Google. They're essentially incarnations of the same idea. The implementation details vary, but let's go through what that idea is. So we want to link explicit data on the World Wide Web in a machine-readable fashion. I think that's one key to keep in mind. We will not, as humans, be able to read all the data that's coming out. It needs to be machine-readable. And that doesn't mean creating new formats for every single thing. This was my view. We want to be able to scale it much like a web has scaled and grown. It's a family of technology standards that play nice together. It's not a single technology standard, and it can drive various applications. So what the W3C has been doing is developing a common set of technologies that enables diverse users, encourages interoperability. And that is, I think, the key theme among these things, that we build a set of loose things that can be decentralized but coupled together by a common API, common standard, common data model. This, the famous or infamous layer cake, is the diagram you'll find if you type the term semantic web, and the first hit would be Wikipedia. And as you can see, it's built on the web. The idea that everything has a URI or an IRI. An IRI is an extension because we don't all speak English, they're different languages. It's an internationalized form of a universal resource identifier. And on top of that, people build XML and RDF. And on top of that are things like rules and ontologies and query languages that interoperate with this. And then you have to put things like trust and proof, which will get us eventually, someday, hopefully, to answering that question. But this is the entire site, and then because we have privacy concerns and other things, cryptography has to come into the picture. So the start of RDF around 1999. That was the idea of the Scientific American article in 2001. And it's taken a while through revisions to get to the point where more and more people are beginning. Skip over here. So one thing to keep in mind is that these technologies are not a magic crank for discovering new drugs. I think, again, there's a hype behind the term semantic web. And we have to get down to what is this and what the semantic web can do and how it's useful for us. Where we are not, we haven't solved all the problems in the semantic web. People are still talking about XML versus RDF, ontology versus ontology. That's essentially the tomato thing that we're still fighting in some ways about how do we define these things, how complex do we want things to be. But what it is, in some ways, is that we have data in various kinds of formats. We can come up with a common representation and some query layers or applications on top of it that allow us to seamlessly attach these. So down to some basic things. What is RDF? I've mentioned RDF a few times that it came out in 1998, the data model for the semantic web. Flexible, use URIs. It's very simple. Subject, a predicate, and an object. Everything is a URI. This is a URI, that's a URI, this is a URI. Okay, let me give some concrete examples. Lee works for Cambridge Semantics. He was born in 1978, and Cambridge Semantics is headquartered in Massachusetts. It's a set of relationships, much like that tree that cartoon figure we're giving in. Because it's a graph, those triples can be expressed together. That makes a very compact representation of the information. So I've just taken the previous set of things and started expanding it to create these relationships, which makes, as you can see, merging data trivial. Remember, we're not saying, one thing to note here is, this is a URI, and a URI has a single address on the web that describes what it is. It cannot be multiple things. So by making it that way, we create a structure where we can merge things pretty easily. And they act, because again, it's a graph, you have nodes and edges, a very common set of things. So what can we do? If things were expressed as URIs, whether they were in a traditional database in one, traditional database in two, or some other form, that graph model allows us to connect things up because we create common semantics across these pieces of information. So we translate these things with semantics, mergers are fairly straightforward. We've all seen CSV files. Then we want to top of it and said, what in the world does this column mean? It happens every day in the sciences. Now imagine if that column took you to a website which said, this is what this definition means. And all we're doing is taking that. So most of the time you see it like this. But imagine you had this relation that there was something which was a customer ID whose name was Travis Ember. That's the notion of the semantic web, that we're creating these relationships. So we created that the person's name is Travis Ember was referred by Janet in the mobile phones. So that's a model, and there's several syntaxes, as with every model. So XML came about because the world lives on XML, at least in the early days of the web. More recently, people have been using Turtle, and as of 2 months back, Trig was formalized as the next incarnation of a compact syntax for this. So I'll give a simple example of Turtle. What it looks like is this. We're still talking triples, subjects, predicate, objects. And wherever you see this colon, it's essentially you take whatever is over here and you place it over here. So it will be HTTP colon because everything is a URI. Right? So this is saying the exact same things we saw earlier. Lee, an employer, Cambridge Semantics, Lee's birth year is 1978, and so on. And you'll be seeing some examples of this in the context of Brainhack.
Wait, I'm sorry, it's not true. You're saying that Turtle is now considered an official standard
Yes.
for communicating this? Really?
That was a while back. Trig is now an official standard.
What?
Which is, so I don't want to go into Trig right now, but I'm happy to talk about it later on. So once you have that data, then you have something called Sparkle. which is a query language built on top of this data model to allow for queries. And you'll see some examples of it in the context of our IBM work later on. I'm going to just skip this for a moment. But one thing Sparkle allows you to do, and it's built into Sparkle, is a read-write mechanism. So with SQL, you can make a query. To get data into it, though, requires other ways, and you can't make this query across multiple databases. So how many people here are database developers? A few, okay. So how many SQL instances can you query at one time? One. Sparkle allows you to federate your query over any number of triple stores, which are the RDF data stores that exist on the web. And they could be anywhere on the planet, as long as they had an endpoint that was queryable. You can run a join across all of those databases. It can be fairly complex when it gets to complex queries, but it's extremely flexible in terms of what the kinds of queries it allows. And it has various other things that come with the web in terms of updates and the REST protocol. So I'm going to stop over here because that's the pieces that you'll need to kind of cover the next few things that are coming up. In terms of just some practical examples of where this is being used. So this is the knowledge graph by Google. It's a set of relationships that come up automatically based on your queries that you put there. They won't say they're using the semantic web, but it's a set that comes from relationships that they store. Right. There's something called the linked open data cloud, which is the current state of linked open data as connected by semantic web technologies. And in this set of relations out here, and this works PubMed, right there. So all of PubMed is available as RDF through Bio2RDF. This is Michel Dumontier's work out of Stanford. And so you can make queries across the abstracts and all syntax, not the contents, because the contents are still behind some tables. Nature is using it for their entire publication set. And what we've been doing is building on top of this with a model called ProfDM, and you'll get to hear extensions of this model. So it's essentially a semantic web model for capturing provenance that we've adapted for things in Brainhack. So I'll stop with that, and without taking questions. Yes?
Yeah, so the counter argument would be that ontologies are inherently brittle and it would be better if we, instead of forcing people to fit their to articulate what they're doing to an ontology, we were running continuous bag of words methods over the free text that's actually there, and eliciting vector scalar relationships among words from the text. In other words, so that we can see how relationships are diffusible, and how the strengths of the bindings change over time or across the space of investigators, and that's what you really need to identify lacunae in the research space, right? If you're trying to do this, not just to find something, but to say, well, what's not being done, to see what's not there. Right? Already, there have been papers published where people are using basic approaches like Jacquard indices to identify gaps in research literature, right? Research opportunities, right? And that, and it seems to me, now I understand that there are non-trivial issues surrounding the compute power involved in running continuous bag of words over over large data sets, right? And that this is the bulk of, for a large part of what Google's research. Without these data, right? How do you regenerate a NoSQL index for the entire web every 4 hours, and with useful fidelity to relationships as they're there, not as people were describing as they were going to put some metadata. But I'm wondering if you can just comment on the tension between the brittleness and ideology-laden nature of ontologies that people make up of that, deductive ontology as and what advances there might be in bringing an inductive approach, compute, where the compute power is invested in building the ontology rather than having people do it.
So there are a couple of thoughts along those lines. I'll start with a paper by Craig Heidegger, the same person who wrote that thing that this is not a magical crank. What he did was, in fact, build a gene ontology based off of papers that matches very well the human curated ontology that was created by a set of biologists working together. So I'm completely in agreement that you can create these ontologies out of analyzing documents. But that still requires interpretation by people in looking at things. So one of the things we've been thinking about is there are many parts to the semantic web. The ontology part was the dream world, that we can create AI in a way we can resolve all kinds of questions on the planet. The oracle from the Hitchhiker's Guide. Except it wouldn't just say 42, but it would answer every question on the planet. However, what we are focusing on are that we have consistency in naming and creating links between data elements. So independent of reasoning on top of it, to be able to discover and search for information. Right now, what does one do? You can go to Scopus and make a search, because that would allow you to search through all of Elsevier's publications. If you go to PubMed and make that same search, that's based on a much more limited set of information. Now, Google is changing the landscape here because it has access to a lot more information that makes those searches possible and updates those information. But the specificity of questions that we might be able to answer, even if you reduced it from that relatively abstract question to more concrete things, would be harder for the current search engines to get back. So I think what we are trying to do is to say, okay, the ontology world is hard, but we can get a lot out of this world just by creating common terms and vocabularies and linking data in a consistent manner that allows us to discover things.
Great, thanks, Sandra. It's actually a really good segue into what I'm going to be talking about. So I'm going to give a quick overview of this large, kind of complicated picture here, and try to break it down into a couple different pieces. This is informatics. There are always way too many acronyms and everything. What I'll be going through is, so a good overview, and I'm going to be talking about something called a data set descriptor, and also an experiment hierarchy model. And so those two pieces allow you to describe an experiment, kind of the kinds of things that you would find in this space. We have like acquisition details and raw data, and the kind of information you would find on the homepage for a data sharing website, like an fMRI or like the Indeed data sets. So what NIDM aims to do is to represent provenance, or how data that is acquired from specific subjects according to some protocol, and the raw data that's collected there, this could also include like neuropsych tests and whatnot, are then processed and transformed into derived data, which are eventually published and hopefully archived and distributed around to the community as a resource. So the notion here is that provenance is a common link that allows you to bridge across these different pieces. I'm not actually going to dive into describing the provenance data model at this point, so I think it's a little bit kind of low-level data model piece that if you're interested, we can talk about it more one-on-one. But to give a very practical example of how one of these vocabularies is developed, I'm going to explain this data set descriptor piece, which I think it'll be fairly straightforward that you'll understand how that relates to what Sasha was talking about, where you have the person that has the tag that says they are a person, and there's a cat, and that these are These are entities that then have attributes that describe certain properties about them. So with that, I can start off by looking at this piece. And when you look at one of these web pages that describes the data set, you usually have some kind of abstract information that tells you about it. You have credits that says who are the authors, who are the people that are actually participating in this research activity, as well as, for this one, it's a multi-site trial, so you have a variety of different locations that are participating in the data acquisition. Scrolling down, you have usage agreements, download sites where you can actually find the files themselves, and as well as some additional places where there are databases that are replicated and funding acknowledgments. So similarly, you might see go and look at the OpenFMRI site, and for a specific data set, you get the same kind of information. You have the title of this task, who's responsible for what tasks, the investigators, acknowledgments, publications. This one has a little bit of extra metadata that's embedded in the page. And so when you start thinking about this URI, OpenFMRI dataset DS001 as an identifier for this information, you can start thinking about all of the different attributes on the page as simply terms that describe different types of information that are pretty common across the different types of data sharing resources. And so if you want to come up with a common way or a format for describing this type of information and provide some best practices for the minimal information that you should be including when you publish a data set, you can start thinking about what are the terms that are used to say, what is the sample size? One site you might have somebody with a by, it might say, number of subjects. Here it says sample size. But how do you know that those two things mean the same thing unless you come up with some standard that people agree upon as a community that when you describe the size of an data set, you use the same term. And so luckily, we're not the only people that are thinking about this. So this is a project that's out of the W3C. So also the standards committee. The number of people that are involved to come up with standard data set descriptors. So none of the people that are listed on here are in the neuroimaging community as far as I tell. But
Put them on this end.
yeah, Melissa handled it. She does this person, so she consulted with us last year. But so these guys are going through to come up with some standard descriptors. Their main focus right now is on a data set called Kimball, which is a chemical database. And there's a variety of other open data sets that this would be applicable to. And so what they're doing is trying to come up with a way to describe how you release a data set. And so they incorporate a number of vocabularies that have already been developed. So we're not starting from square one and investing tons of time into developing the perfect ontology, because a bunch of people spend a lot of time doing that, and there are much more lightweight ways of kind of getting the benefits of using RDF without having to invest this huge overhead of modeling everything perfectly and ending up with more or less a Braille system. So with this flexibility in mind, one of the proposals that they have is this simple little setup here, where you have a couple different levels of your description for a data set. So you have a summary level description. So this is information that doesn't change as new releases of the data set come out. So those are static things like the title description. If you have a longitudinal data set, it would not include how many subjects are in there. So it's just static for a single, for the entire project. And then there's a version level description where this goes into the specific release information. And so they have a version number and a couple other attributes like what the date was when it was released and a few other things. And then you have this other level, which is the actual distribution level, which has things like the download links of where that specific version is located, etc. And so an example of this that I worked off of the OpenFMRI data set. So sorry to scare you with actually showing you what a turtle document looks like. But I think it's fairly readable and it's meant to be readable. So just to kind of orient you to what this is at the top, you declare all the different types of vocabularies that are being used. So you have basic RDF vocabulary, and then there are other ones for that's called doubling for and folk, which is a friend of a friend for describing people. the provenance ontology. And you kind of can stack these in. It's more like importing these vocabularies into your document. We also describe one for OpenFMRI. And so this is a local vocabulary that's just specific to OpenFMRI, or if they want to include extra annotations or information about a given data set that is not part of these other vocabularies, nor is it part of this healthcare life sciences working groups definitions. But that doesn't mean that you can't include that additional information. So what does the OpenFMRI entity look like? So OpenFMRI has a number of different data sets, but just if you want to describe the resource itself, so just OpenFMRI and all of its contents, you can say that it is a data set. So this little A is quite literally saying that this piece here, OpenFMRI, would map to that openfmri.org dataset location. And then saying A is like literally saying it is a dataset and it is a provenance collection. And then there are a variety of other attributes. I won't go into the details of these guys, but these are things that are defined in this HCLS specification. But there are a couple things that should stand out to you. Like one, you have a description of the data set. You have an identifier. It says that it's in the English language. There's a license associated with it and a publisher. And then you can include things like the rights information and what the source is, title, etc. You can include a logo using schema.org, which is one of the vocabularies being developed by Google in collaboration with a number of other search engines. And associate keywords, themes, etc. And one of the things that you can also have here is that there can be a has-part relationship. And so within this has-part relationship, you have a list of all the data sets that OpenFMRI contains. And then you can go into more details describing those specific data sets down below. So for one data set, as an example, you can say that this conforms to this HTLS data set descriptor, that you have a specific creator, what version this is, what date it was issued, etc., and where to access that information. And so you can go down and kind of get to these fine level detail of just describing that data set and where it's located without describing its contents really. It's just more like its existence. And so that point is just that you're coming up with a standard way of describing more or less the same kind of common information that you find on different pages that are doing data sharing. So in the data sharing pages, you find a very common set of information that you find elsewhere, but everybody uses their own descriptions, their own vocabularies, their own text to describe it. And by kind of extracting that information and mapping it to these common terms, you end up being able to write like a single query that will now work across multiple different data sets. And like what Sasha was talking about earlier, if you have these descriptions, you can then distribute them out. So you can start thinking about the aggregation services that if you start coming up with these common descriptions of the data sets that we release in the community, without even releasing the data sets themselves, right? So it kind of gets over some of the data sharing issues. But just releasing that metadata information, you can start aggregating this and building apps on top of it that allow you to see like what is out there, without having to go through the laborious task of actually manually mapping everything. But it has to come down to people agreeing upon starting to publish the data using these types of standards. And so there are a couple other levels here. So if I go back to this diagram, so that's this kind of data set descriptor that describes the actual data resources. And so there are also, you want to be able to dive down and describe the specifics of each of those resources as well. And so you can think of something like an XNet database where you have this is a bad URI. This is used as something like 2014. So when describing a specific data set, you again have this unique identifier for this file, and then you have a bunch of attributes that are all over the page. Specifically, it has an identifier, a description, a title. It has a list of subjects that are contained within that. And then you can drill down on these things and see that if you look at a specific subject, that they have experiments that are associated with them. And if you look on the experiment page, the experiment itself has another URI and some additional attributes. So this one has specific types of scans that are associated with it. So if you think about this in the same kind of context as that turtle document, you can start looking at the H2O page not as this kind of presentation layer we currently see, but as it is actually made up of kind of these common data elements that underlie the database itself. And so one of the things that we're working on, so this is one of the earlier projects, you'll hear about something that's a little bit more developed next, is coming up with common ways of describing data sets, so the full database, but then also drilling down and being able to provide specific details all the way down to scans and being able to have information, for example, from the DICOM header. And by representing this in RDF, it allows you to start using these Sparkle queries to get at information that you normally would not be able to query in many of the different data sets that are out there, or databases that are out there. And that would be a good transition over to some of those data results.
Yeah, so you could describe basically your own experiment using this data, right? So yes. But what about the infrastructure? So where would I put query? I mean, this allows you to go query on the search and the data. Whatever. Right. Do you kind of propose certain infrastructure to offer to do that? How to make it a more like individual and set matter of the first how do you do it and how to think about copying them?
But you're talking in terms of the specific queries themselves, of like how you expose like a view of a data set. Yeah, I mean that's something that we've been working on as well. It's something we can talk about afterwards, but I have in another project that we're calling more or less like an IDM query project. We have another metadata standard for describing queries. And so it's funny because you can describe the query, describe metadata about the query using turtle documents as well. So it's just like turtles all the way down. You use a query that document to see what types of information you can create. And so it's it's a very elegant framework that a bunch of very smart people spend time. I mean, the engineers of the internet are the people that are behind this. And we're just kind of filtering off their ideas and looking at how they're applied within our domain. And so, the infrastructure piece, we have a few things we're working on, but it's still very early on. We have some different apps that we can
Good. So just start by going back to the whole overview of the NIDM components. So as you can see, there are several of them in there, and what we're focused on now is NIDM results, which we've been working on more precisely for about, I would say, a year now. We've been focusing on that component. And one of the interests that we have in modeling these part of the data is that we would like to have some format to be able to do meta-analysis afterwards. So, as you can see on this graph, the NIDM results component covers part of the analysis and workflows, model the derived data, and also part of the data that you would usually put in a publication, so typically a table of coordinates and a statistical estimate. So if we go a little bit in more details, where are we right now? Right now in NIDM results, we have a specification that covers model fitting and inference. So that means that you'll have the design metric associated with your particular model. You'll have all the effect estimates, the standard error, the statistical map, and then on the other end, after the inference, so you get information about which threshold have been applied to your data, and you get a complete description of all the peak and clusters that you found, if you found some in your data. So here is an overview of what we have now, and in fact, we have worked both with SDM and FSL, and we have common model for both and some specific element that will be available only in some software because all the information is not available in all softwares. So if we go again here on the right, you have the global overview. So you have statistical estimation or model fitting and the inference part, and describe using the pro data model. So we have a couple of activities: model fitting, contrast estimation, inference, and we have a couple of entities that are either generated by these activities or used by them. I don't want to go into all the details, but of course, for each of these entities, you have a given number of attributes that gives you more information about each of them. In terms of implementation, right now, as I said, we have a model for both SPM and FSL, and the export is natively implemented in SPM, and we have some script to export FSL results in this NIDM format as well. Our next goal, I think, would be to work with AFNI to see how the model, how their particular data would fit with this model, and what do we need to add or change in order to make it generic enough. When it comes to the hackathon, so when we came here, we decided to have a bunch of examples. So we have made available on the website a bunch of NIDM export that we can use and start seeing what we can do with that. So we already started to talk with Chris to see how Neurovault could use this format in order to upload data. And I think one other point is also to get feedback from you, from the community, to see what, if you want to have a look at what we have right now, what do you think is missing, if you can think of things that are modeled properly, or if you're just curious about what's in there, I think we'd be more than happy to discuss that. And we have a specification document that describes in a more formal way what's in there, but I don't want to get into that right now.
So you gave there was an example there where you said something like there's a cluster activity and gives peak and all this kind of stuff so if somebody were to want to add something more to that, they wanted to say something about a cluster. Would they work with you or somebody to be able to add to that, like a Dublin core type thing, to add to yours? Or would they create their own and just call their own and call yours? I mean, is there a certain place where people should look to try and contribute?
So I think it depends what you want to do with the model exactly. If it's interact with SPM and FSL and change it in there, probably one way to interact, at least with us, would be to send something through GitHub, like an issues that we can discuss. Maybe the model just needs to be updated, or if it's something completely different, then I think you can just add entities and link to what we already have, because that's what Symantec is about.
But the terms that would be used there are generic, independent of FSL or AFNI. So if we're talking about a cluster and a peak or something like that, is that something that would then have corresponding entities in each of these different packages, or like the peak may be defined differently by different packages or derived differently, or
So the derivation should be modeled through the different activities, but we try to put in the NIDM namespace the entities that we thought were common across software. So a peak is one of them, and it's in the generic namespace. I don't know if it answers your question. Maybe you want to...
Yeah, I think what Emilio was saying, that the derivation, so the provenance of that peak is modeled. So you can always query for peaks that came from SPM versus peaks that came from FSL.
So it's in the context of the graph that you get its identity, not any given name.
So I'm going to quickly talk about Neurovault and how it's so fantastic. So all of data sharing is about sending non-short terms and hence fiction. But I'm talking about very specific problem in data sharing case. Do you guys recognize tables like this? Those are tables of coordinates. So many papers published every year in human neuroscience look at neural correlates of different cognitive skills, states, diseases, etc. And they report those as peak correlates. They perform their analysis properly, they do inference, they correct comparisons, they find blocks in the brain and report where those blocks are. And thanks to standardization, we have those in either MNI or diagram space. And we have this. But when you think about it, and that was already very nicely put yesterday, I think, Tom, that so much effort was put into those studies. So much work has been done, so much data has been collected, and at the very end, we're still into those 6 to 12 pages of paper, out of which, let's face it, like at least one third is subjective interpretation of data. This is the most useful machine readable piece of data that is included in the paper. So one can think, why are we basically throwing so much money? Why are we wasting so much money? And the problem is that because we are trapped in an ancient form of disseminating data, disseminating knowledge, which is the paper. We have to put everything in a format that used to fit a journal, and now we also have to distill our knowledge into a form of a paper. So that obviously calls for data sharing. But data sharing is a bit like flossing. Everybody talks about it, but no one does it. Yes, thank you. And there was a laugh somewhere there. Okay, yes. So I do applaud the only person not saying that. So yes, we all agree that data should be shared, and we all know that's good. But the problem is that almost no one does it. And well, let's say this talk was prepared for a different crowd, because in this crowd, a lot of people share data. But on a bigger picture, data sharing is not that popular. And there are reasons why that. Well, the sharing data involves work. You prepare your data, you have to make sure data is described in a way that it makes it reusable or actually useful for other people. And there are, of course, the risks. People are afraid that if they're going to share the data, someone else can scoop them, someone else is going to find a problem in the analysis and undermine the results, etc. So, as you probably already figured out, you're proposing a new database. And all these problems, somehow we are claiming that we are trying to get around them. But before we go into more details, I'm going to quickly start on the topic of, well, not the database, yes. The same thing with the standard databases and data sharing initiatives have been proposed in our community. And I'm just going to quickly talk about SMRTC, which was probably the biggest attempt to kind of standardize and make data sharing a mainstream thing. And unfortunately, it ceased to exist. And the thing is, the big thing is it's not a success at the moment, is because it was a big technical challenge at the moment.
Because more, he'll tell you because the government funding got pulled out of it.
Yeah, but I think that you will need less resources right now because the technology is
better, and as spoken about
yeah, and also the other argument I tried to make as well that the initiative wasn't very ambitious, and that's why it was required so much resources. Very raw data, very all data sets with description, especially complicated data sets, because Ethermarks was about sharing task-based FMR study, which require quite specific descriptions of the task for the data set to be usable. Requires a lot of curation, and that also consumes a lot of.
You also have to get this man. You had like a bunch of diagrams on this that had to be deciphered. It was really difficult.
You have to make it do that.
Yeah, they made you do diagram files on this.
Yeah. So I think that there are two aspects of that. One, that technology is moving forward, and the second, that this is a very difficult type of data because it's a complex data set that requires a lot of curation. And of course, like, the main problem was as Mike said, the government funding was pulled out. But I think that the complexity of the data and lack of technological solutions at the moment will happen. And don't get me wrong, I think it was a great success considering how challenging the problem was. So what we are trying to do is we are trying to do something much less challenging. To focus on data that is easier to capture and much easier to share. So we are trying to like data sets. So we're trying to minimize the cost and at the same time give something in return to the user. So we're trying to capture statistical mass. So not the whole raw data set. And something step before the paper. So not the coordinate table, but unthreshold statistics. And this allows us to perform much more powerful meta-analysis. Because now we are able to find effects that are slightly sub-threshold, but consistent across studies, which is not that unusual. It's not something that should be surprised about, because most of the studies as now are undercover. And we're trying to minimize the cost by just asking people to upload their statistical maps and provide the DOR paper, because at the moment the paper is the best known existing description of the data. And we try to streamline the process, we make it easy to use. There's like waste logging with Google and Facebook and whatnot. And in return, what we give is an interactive web-based visualization of this data, something that they can share with their collaborators, something that makes their data look better and is more attractive to the reader. So basically, what we're trying to do is to keep the cost and the benefit very low. And this is how the database looks like. And literally, you should go and try it yourself. You can upload the data sets that are not published yet without DOI as well. Just to play around with it, figure it out. Literally, it takes 5 minutes to upload the data set. You point to a folder on your hard drive, it uploads everything and checks what is in the nifty file, puts it in, and then you have very good visualizations. And we recently included a 3-dimensional interactive visualization from Jack Gallant lab, which is very fancy and very appealing, and it allows you to go from volumetric data to surface. All of that is online, doesn't require any plugins to your browser. You can do lightly surfaces as well as flattened surfaces. So what I encourage you to share stat maps and make science more reproducible. And how and how does it relate to everything that was told right now? So an IBM standard allows to describe the results of inference, results of the study, described in a very formal way, which means that a lot of things that people care when doing meta-analysis do not have to be put in manually by the people uploading the data. So we can infer a lot of things from the data because, as Tom mentioned yesterday, the software already knows a lot of these things. A lot of these questions that are so important are already answered during the inference process, and the information is there. So now with the standard capturing this automatically, has been built in SPM right now, and through applying into the net itself, we are able to capture that. And today, with Camila, I managed to write my first turtle, instead of the turtle query, which is this UTD. It's not Spark. It's Sparkle. No, the data set is Sparkle. Okay, yes, this is how much of an expert I am. Semantic web, by learning. This is what it is. So I wrote this Sparkle query on a turtle data. Which gives me this, which gives me information about the space in which this particular study was space in which the results are, the type of the statistical map it is, the file name of it, the name of it that was given by the user, and the vector describing the contrast, which shows something, and we can extend more and more. The point is that this doesn't have to be now put in manually by someone uploading maps. Well, and this is it. So I thank you for attention, and hopefully you're going to go to your vault and have a look at it, share your opinions, and share your feedback. That's great.
Well, I want to thank Chris for updating my talk. So that's, I was just going to show a query. I think we've run long enough, so I'm not going to do it. If anyone's interested in learning more about these queries, come see me. And you want performance queries? I think we would
So you mentioned Judy,
That's an excellent thing. Sorry, I forgot that.
I'm sharing too.
Thank you for reminding me. Yes.
But
that's great. Everything.
That's good. Thanks.
So I'm going to read just that. So there's Cameron product on the line. Cameron has all hackathons. He's actually the guy who came up with the original. Yeah. The original. Oh, read the microphone. Hello. Okay. He's not going to use the microphone. So anyway, that Cameron, you are going to go in front of everybody now. Cameron! Okay, I'm going to turn you around, but first I'm going to give him a voice.
Can you say something, Cameron? I think we heard you.
Yeah, can you hear me?
Yeah.
Is this thing on?
Yeah. And now you're going to see who you're talking to.
Right. Hello, everyone. So Pierre and I, thank you very much for Pierre for arranging this. Pierre and I have been working for probably about 2 years now on the Abide Pre-Processed initiative. And the goal of this initiative, as we've done before with the ADHD 200 data, is to share, to pre-process the entire Abide consortium data and to share it, the pre-processed version of the data. And so our goals with this are twofold. One goal is to get data to people who may not know about may not know how to pre-process data to get data into their hands. So, maybe like statisticians or computer scientists or mathematicians. But also, our other goal is to actually kind of be able to compare different. Can y'all see my web browser?
Yeah.
Okay, good. But and also our goal is to be able to compare different pre-processing strategies. So Pierre and I and two other groups of people have pre-processed this data using their favorite pipelines. And the data is now available. We're loading it up on S3. So Nolan Nichols and Satya Ghosh arranged to have everything accessible on S3. And we wanted to quickly present it here to you today so that possibly if somebody was interested in using it during the Brainhack, they could use it. So right now, as I mentioned before, the functional data has been processed with 4 pipelines. So that's my pipeline, which is CPAC, Pierre's pipeline is NEAC, and then there's also dparse and CCS, which are some other popular resting state type analyses. We also have 3 structural pipelines. We have ANTS, cortical thickness extraction, we have FreeSurfer, and we have Civet, which will be going up hopefully soon. And Arno, we haven't run MindBoggle on it yet, but we hope to soon. But just to give you a quick idea, so here, I don't know if you can see it or not, but it's the URL is kind of long, but it's preprocessed connecthomes.github.io/abide is where the web page lives. Apologize for the long name, but PCP unfortunately was taken. But so we've done, one of the things we try to do is, so if we get the data and it's only pre-processed, then, quality assessment becomes much more of a chore because you don't necessarily have the raw data. So one thing that we've done is try to go through and give, kind of different levels of quality assessment. So a member of Pierre's lab, Yassine Ben Ajali, went through and very carefully looked at the raw data, as well as how well the data was normalized. We have other individuals that went through and spot checked the derivatives to make sure like the ALFF and the VAMC values weren't crazy. But here, if you look at the QA page here, it describes how some of these were done, I think down here at the bottom. But also, one of the things that we've been working on is developing a protocol for doing quality assurance, or quality assessment, that is. And so what we've come up with is a bunch of metrics that we've calculated, that we found in the literature that people have proposed before for either fMRI or MRI data. And we calculate a lot of those on the data without any real strong preferences as to which one might be better or not. And so our goal is that maybe through machine learning or comparing those measures with the measures that we got from the hand assessments, we can learn more about these and determine which ones are more important to use or more useful. So to show you really quickly, there's if you look on the Abide page, we put together a brief tutorial about how you would use the data using the Amazon or using AWS with your free $100 credits, if you like. And if you look here, there's kind of embedded in here the information how you access the data right now. And please bear with us. This is kind of in progress. And we just put something together quickly so that y'all can find it and use it. But we have a script that we've written that is available. So the page is on there that shows you essentially how to format a string in order to get the data. And so the data reported from pipelines are there, and for each pipeline we have 4 strategies. So for the majority of the choices, like the type of nonlinear registration algorithm, or whether or not you do scrubbing, many of those decisions were left up to the specific pipeline and to the groups that were doing the pre-processing. But each one of the pipelines produced 4 strategies, with and without filtering and with and without global signal correction, because those tend to be, those are 2 of the things that are highly controversial. And then in addition to that, we ran all of the derivatives that we calculated. We ran those through the same pipeline, so those were all calculated through CPAC. So the only thing that's variant between these is the actual preprocessing, not the math that was used to calculate the derivatives. In terms of derivatives, we've released, I believe it's somewhere near 19 derivatives per data set. So there's FLFF, LFF, Reho. There's just a bunch of different ones, and that information is on the website as well. So I think that's about it, unless you have any questions.
Is there a question?
So let me know if y'all want to use the data. We're hacking away here in New York City. Definitely we'd be interested. If any of y'all want to help us look at the data or write tutorials on how to pull the data into like iLearn, do classifiers on the data, or anything of the like, we'd definitely be more than happy to work with.
So there's no way to query on the metadata of those things yet, right?
I'm sorry, I didn't hear you. Could somebody repeat it?
So, I mean, if you had used NiFi, for instance, you have the metadata of the processing, right?
They use NiFi for some of it, so for the other thing. We have some provenance, but it's not in like a unified format.
Thinking of CPAC is developed using NiFi, if that answers the question. But all the data is in a format that can be used, I think, with anything easily.
Well, I guess because so Cameron, we just had a session on like provenance and how to share data in a way that are reusable. We have 1,200 subjects times 4 software packages times 4 preprocessing strategies times 19 outcome measures that we're releasing. And yes, you can't really track automatically exactly what was done. And some of this information is saved. I think for CPAC it's safe, for NIAC it's safe, but under various forms. But they're pretty extensive.
So I'm just asking the question to I believe that maybe one step further for like our work team. So try to find standard for describing those things and referring to them.
No, yes.
So we need to figure that out. And frankly, Davey, this is kind of your wheelhouse. I think Nolan's going to help figure some of this out too with the data that we put up there in Slideshow. Right now with CPAC, for each pipeline we calculate a hash over all of the parameters that are given to it, so that we can give it a unique ID and use that. So if so it's an alphanumeric string, and then we take that string and we use it. We index a database with it and give a city name corresponding to that string. And then from that city name, that's a unique specifier that uniquely specifies a set of parameters that were given to CPAC to run. So if I give you that string for my pipeline, then you can use that, and you can recreate the exact identical pipeline that I used to run, which is one step forward, right? But I agree with you. We still haven't got to the point with this data where somebody can, at least with the data that we're releasing, where somebody can actually track the provenance. They just kind of have to take for granted what we tell them.
And also, just to maybe just make a comment, it's like you can have a strategy where you change every possible parameter, and it's a huge parametric space. And our strategy was more to say, you have the software groups, they publish with that stuff, and we are taking, they're not comparable. None of the tools I've used are used by Cameron's pipeline, and I think like the Chinese folks have used SPM. He uses like ANTS and AFNI. I use Mink, which is basically an outlier in the world. So they don't fit. So I think we can just comment convergence. Divergence can come from a lot of different sources.
The question I was asking really is, once you've got those results, then what are the parameters? What are the things that are really important for getting? How do you assess your test? That's what you were talking about, like machine learning aspect of that. And then, how do I guess what are the parameters? And if you can't query on things, then it makes it harder. But yeah, I understand.
Cameron, do you want to answer that one? You hear?
I'm sorry, I'm having a little bit of trouble here.
Okay, so Jean-Baptiste was really wondering, like, how can you compare, try to understand what are causing differences when there are differences, and I think at this stage it's more to to assess the extent of differences, not to nail down which step or parameter is causing it. Also, maybe to try to find invariance. I know that the motion estimates we have, at least across CPAC and NIAC, are fairly consistent. So they are, not everything is completely pipeline dependent in that, which I was surprised. But no, yeah, I can see how in the future that thing is, get deprecated really fast. But I don't think there's a resource out there that's even remotely that. I mean, there's the HCP that has preprocessed data, but there's like one strategy.
That's a great thing.
I mean, yeah, I think that Pierre is exactly right. We're not systematically varying one step at a time between them. So right now we're just being able to evaluate. Actually doesn't matter, right? And it's kind of interesting. Some of the preliminary results we have, and we'll be putting this up on the webpage soon, is we actually see, so we have 4 pipelines, and then within each pipeline we have 4 strategies. And what we found is actually the amount of variance between pipelines is greater than the amount of variance between strategies, right? So whether you use NIAC or CPAC matters more than whether or not you use global signal regression, for example, which I think is kind of a big deal. And I mean, to me, it kind of is a little bit eye-opening. I think that probably the biggest sort of thing that injects variance into these data sets is how you spatially normalize the data.
So, Cameron, if that's the case, can you use the 4 different pipelines with each using the other spatial normalization algorithms to test that?
Did you hear the question?
I think that whether or not we haven't done any of those things.
Cameron, in the CPAC, you can do ends versus third, can't you?
Yeah, you could test that within CPAC, I guess. That's my experience.
Well, okay, so as Mike brings up, we have done that between NERT and ANTS. But a lot of the NERT outputs that we got, they were, I mean, put it this way, we tested for NERT and ANTS and ended up releasing the ANTS. We didn't think that it was a fit for these NERT because the quality was fairly poor.
But Cameron, I don't know I use NiPipe and I don't know the other pipelines. Can you use ANTS to normalize in those others just to be able to at least make that comparison?
Well, it's not easy to move deformation field around. Like there's NERT and the FSL tool, Dartel. I'm not sure how much they can.
No. What all I'm saying is that not the.
Like if you could feed a NERT transform grid in SPM with sampling tool, which I'm not sure how easy that is, maybe, but we haven't tried that. NIAC actually can use ends,
yeah.
So that's definitely an option. I see. But it depends on the capabilities of the different pipelines. Like,
I don't know, it would be fun if we did all these comparisons. What would we do if we didn't do these things? We love something for you to help get involved with us on this stuff.
Sounds good.
We'd be more than happy to use your expertise and
we started that.
wrangle these tools together to do those evaluations.
Okay.
It took us 2 years to get to that point. 2 years ago, we had a project on QC on Abide.
Yeah.
With Mike, Cameron, and that's the end result.
Wow.
Where we went.
Wow.
All right. Okay, I think that's all for today. Thanks so much, Cameron.
Thanks, Cameron.
Thank you, everyone. Very nice seeing you all.
So I guess that's the end of the data sharing session. What's the next thing?
The next thing is tonight.